Okay, I think we are ready to go. Hi everyone, and thank you for joining us today for this webinar organized by bleenc, bleenc, the next generation BLE RTLS platform. Let me introduce myself. I'm Arianna Buccero, Marketing and Communication Manager of bleenc, and today we'll be talking about bleenc, bleenc new real-time location platform. Before we begin, a quick organizational note. There will be a Q&A session following the presentation where we'll answer all your questions. And for any question we can't address during the webinar, please email us. Great. Let's get started. Let's begin with an overview of the topics we'll cover today. We'll begin with a brief introduction of bleenc, providing context of who we are, what we do, and our position on the market. We'll then move into the world of RTLS solutions, explaining why we choose to specialize in the development of Bluetooth Low Energy-based localization technologies. We'll continue with an in-depth look at bleenc, highlighting all its distinctive features, and we'll conclude with some concrete use cases, exploring the most relevant applications. Before moving on to the main topic, I'll introduce you who we are. We design and manufacture IoT devices, systems, and solutions for identification, localization, tracking, and monitoring. We have an in-house research and development department covering hardware, firmware, and software development, which allows us to offer complete and highly customizable solutions. And let's conclude with some numbers that illustrate our experience. Over 500,000 devices sold and more than 1,500 customers in over 50 countries. Let's now move to the core of the webinar by introducing what an RTLS is. RTLS stands for Real-Time Locating System. It is a system that allows for the real-time location and tracking of objects and people within a defined area. And they are also referred to LPS, local positioning systems, as opposed to GPS systems, which operate on a global geographic scale. The operating principle is simple. Tags are attached to the objects or people to be tracked. The tags communicate with a network of fixed antennas installed in the environment. Software collects all the data and calculates the estimated position, updating in real time. In general, RTLS systems can be used either indoors, such as factories, offices, hospitals, and warehouses, or outdoors, such as construction sites or parking lots. The main applications are distributed across various sectors, including manufacturing, intralogistics, offices, and healthcare. And within this context, solutions can be used, for example, for monitoring the progresses of activities and processes, locating assets, goods, or devices, tracking vehicles and mobile resources, or also for access control and attendance management, for monitoring space occupancy, and for example, again, the safety of operators and patients. As you can see, the applications are extremely transversal and cover very different sectors. So let's now delve into the more technical aspects, starting with a general framework for RTLS systems, which highlights the fundamental components common to all localization solutions. At the core of the framework, there is the hardware component, composed of mobile devices known as tags, which are attached to people or assets to be tracked, and the fixed infrastructure composed of antennas, which we can also call anchors or gateways. Indoors, antennas play a role similar to that of satellite in GPS systems for outdoor localization. It's important to emphasize that this is intelligent hardware, meaning these devices also integrate the software components necessary for their operation. Moving up to the stack, we then find the software component, which represents the heart of the system. This includes the project configuration and management tools, the user interfaces for data access, and the most important, the positioning engine, which processes the signals and estimates the position. Finally, RTLS systems generally provide communication interfaces, such as APIs, based on IoT protocols, for example, HTTP or MQTT, that enable integration with external applications. This framework represents a valid reference model for all RTLS platforms, regardless of the technology they are based on. Today, we'll focus on RTLS solutions based on BLE technology, and in these systems, communication between mobile devices and the fixed infrastructure occurs via Bluetooth Low Energy standard. It's useful to briefly introduce the role of BLE in localization technologies. Bluetooth Low Energy was not originally developed for location applications. It was designed for proximity communication. However, starting in 2014, with the introduction of iBeacon technology by Apple, BLE also began to be used for applications in localization. Initially, these applications were related to the mobile world through smartphone apps. Over the time, however, the technology has evolved, finding application in various contexts, including industry and healthcare. This evolution has been possible thanks to a series of BLE strengths. First of all, scalability, both in functional terms and in size terms. Another key element is the low cost of the devices. In fact, BLE tags are generally much cheaper than those based on ultra-wideband and proprietary technologies. Then there is the issue of flexibility linked to the possibility of integrating additional features beyond localization, such as environmental sensor, for example. Let's not forget the long battery life, thanks to the low power consumption. Furthermore, an important advantage of BLE is its widespread market adoption, thanks to the integration of BLE in smartphones for more than 10 years. Finally, it's a technology natively designed for IoT applications. At this point, we can move into the more technical aspects, and to do so, I will hand over to Engineer Cucini.
Thank you, Arianna, and thank you everybody for attending this webinar. So let's go forward with the topic, and by starting with the design of our new platform, bleenc. So when we started the bleenc design, we knew the strengths of Bluetooth Low Energy for RTLS, but we were also aware of some limitations that affect many RTLS platforms based on BLE. Some of these limitations are here listed for clarity. For example, many BLE RTLS platforms use non-secure transmission formats. For instance, they use iBeacon or Eddystone packet formats that does not support any type of encryption of sensitive information or any type of device authentication. So privacy and security may be a concern for some of the system. Another limitation of many BLE platforms is that they do not support two-way communication. So the tags that are attached to assets or worn by people are just simple transmitters, but they don't have the capability to receive data. So there is no two-way interaction. Many RTLS platforms are wired-only infrastructures, so they need a network of BLE gateways that require both external power and network connectivity. So this means that in some cases, the infrastructure cost can be relevant. And finally, some solutions on the market are realized as a patchwork solution. So they are implemented by taking gateways from one vendor, tags from other vendors and by simply adapting software to the hardware functions. So there is a lack of integrated design. And indeed, the integrated design was the core fundamental, one of the core fundamental features of bleenc. First of all, I would like to explain why we call our new platform bleenc. So bleenc contains the reference to BLE as the standard for communication, but also sounds like bleenc, referring to the capability to send commands to tags to enable light blinking on a tag. And this features is mainly related to the capability to support a bidirectional communication between tags and gateways that can be used for sending commands or configuration. Another important feature of bleenc is related to the security and privacy aspects, so that the communication, the wireless communication, but also the communication between the gateway and the system is fully encrypted and based on authentication of devices. bleenc support an hybrid localization infrastructure. This means that the infrastructure is partially wired and partially wireless. So this allows to reduce the complexity and to have a very scalable solution. But at the same time, it's fully Bluetooth compatible. So it's possible to track and monitor any BLE device also from third-party vendors. And one other features that we have integrated in bleenc is the support for e-paper labels. But let's go in more detail about these features. The first one is the capability to support a two-way BLE communication between tags and gateways. And the important feature is that this communication is extremely energy efficient. So the impact on the battery life of the tags is really negligible. The bidirectional communication is capable to enable many use cases within the localization platform, like transmitting high priority packets with ACK request, or sending triggering commands to tags, for example, for blinking a light or for vibrating the tag. It is able to support bulk configuration of tags. And in general, it can enable complete interaction between tags and the surrounding environment. So we can create context-aware localization solution using the bidirectional communication. Another important feature is related to security and privacy. So bleenc supports high level of data protection through a native BLE encryption based on encryption of data and rolling of the MAC address and device authentication. So this means that you cannot clone a bleenc tag, and you cannot spoof the data that are transmitted from a bleenc tag. Very important to point out is that these features allows to be bleenc fully compatible with the Radio Equipment Directive Delegate Act that has imposed cybersecurity requirements for radio devices. These requirements are important are crucial in those applications where you have people tracking or you transmit sensitive data. But bleenc is not a closed system. bleenc is designed to be fully compatible also with third-party BLE devices. So the bleenc gateways can receive BLE advertising packets from any BLE sensor or BLE tag on the market. And this allows to have not only an RTLS platform, but to have a fully IoT capable platform. So this allows to integrate sensor, for example, like sensor for door opening or sensor for presence detection, but also allows to track BLE paper labels that are emerging on the market. And finally, in bleenc, we have integrated the support for writing data on e-paper displays. And this allows to have only one platform for both management and tracking of e-paper tags. And this open up bleenc to many applications, especially in manufacturing and logistic applications. If we refer to the bleenc architecture, so essentially it resembles the classical architecture of any RTLS platform, where the three layers are included from the bottom to top, the mobile devices, the fixed antennas, and the software. More specifically, in bleenc, the bleenc tags can be either wearable tags or asset tags, and they can have bidirectional communication with the gateways. But at the same time, mobile tags can be also any BLE device from a third party, can be like labels or tags. The fixed infrastructure is composed by gateways that provide the communication capability and also by beacons, and we will see later which is the function of beacons in the bleenc architecture. And finally, we have the classical software on top of the entire system, which includes all the functions from the web user interface, management tools, the location engine, and the support for API for bleenc integration into software and applications. Let's focus now on the localization infrastructures that maybe is one of the core innovations of bleenc. So as I mentioned before, bleenc support a hybrid localization infrastructure, where hybrid means that the infrastructure is partially wired and partially wireless. The wired part is composed by a backbone of gateways. Specifically, we will refer to this scenario, which is, for example, an hospital department, but it can be as well offices or similar applications. So in this case, the backbone of gateways is spread along the hallways, and the gateways allows for real-time tracking of all the tags that move inside the department. At the same time, can receive in real-time signals coming from any kind of BLE sensor or other tags. So the network of gateways is restricted to only a limited part of the operating environment and allows for real-time tracking. At the same time, we have a second layer in our infrastructure, which is realized by battery-powered beacons. So these are essentially BLE transmitters that create a network of devices that are used for what we call snapshot localization. So snapshot localization means that the localization with a more precise accuracy is realized based on different kind of policies. It can be on demand. So this means that by sending a downlink command from gateways to tags, we can ask for the snapshot localization. It can be based on event. For example, every time a button is pressed or the tag stops moving, we can get the snapshot localization, or can be periodic based on a interval based. So this snapshot localization is based on the information that tags collects from the beacons. And this allows for like in this example, sort of room accuracy of the position within a complex environment. This is the present state-of-the-art architecture of bleenc. One of the improvements that we'll launch in the next months will be a simplified version of the backbone of gateways based on a Wi-Fi mesh connectivity, where only one single master gateway is directly connected to the local network, while all the other gateways that are called slave gateways are connected to the master gateway through a Wi-Fi mesh connectivity. So this is useful in many cases where there are connectivity issues in the operating environment. But it's very important to compare the standard bleenc localization infrastructure with a typical localization infrastructure that is used for BLE RTLS platform. In a standard BLE platform, it is required to deploy gateways in each environment. So in this case, we will need gateways in all the rooms. This creates complexity in the sense that the number of gateways increase and the length of cabling increase. If we compare indeed with bleenc, we see that in this case, rooms are just covered with battery-powered beacons, while the real-time tracking is limited to the hallways. With this such kind of solution, we have a huge reduction in the number of devices. We have a huge reduction in the wiring, but this also has an impact on cost of the system and on time for installation. And what we have typically seen in average projects, this leads to a saving of up to 40% in cost and 30% in time saved for installation and design. With this table, we summarize all the difference between bleenc and the standard RTLS platform based on BLE, with all the features that bleenc natively support, but you cannot, or maybe you may not found on a standard BLE platform, ranging from the bidirectional communication to the encryption of data and so on. I would like also to underline the point related to the battery consumption. So with bleenc, we have also optimized the use of the radio inside the tag so that the battery consumption is really reduced compared to standard BLE tags. So this means longer battery life and lower maintenance cost. In order to see what kind of use cases we can enable with bleenc, we refer again to this scenario, referring to an hospital department. Clearly, bleenc as an RTLS platform include all the typical use cases of localization infrastructure, going from tracking of people and localization of assets. But with bleenc, we can also have some specific application and specific use cases, especially related to safety, to real-time monitoring, and to control and integration of IoT data within a single infrastructure. Let's start from some applications that are related to safety. So, for instance, with bleenc, any people involved in the project can wear a wearable button, and when the user press the button on the device, the tag immediately sends a real-time notification with the type of pressure. So the bleenc natively support different type of pressure, from single to double, triple click to long press, and up to 4 buttons on each tag. And the tag, the button event are always transmitted with HOC request. This means that the packet is transmitted until the tag receive confirmation of receipt from at least one gateway. After this transmission, the tag can also provide pinpoint location based on beacons that are nearby the tag, and then can provide a room localization. So in which room the tag is located. This allows to have precise localization of alarm event within, for example, an hospital or an office building. But the alarm call can be furtherly enriched by providing feedback to the user. So when the user presses the button for the real-time notification of an alarm event, it is possible, using the bidirectional communication, also sending a notification to the user that can be a vibration on the tag, or a sound, or flashing of light, so that the user is aware that alarm has been received by the system. So this provides more safety and more confidence in the system from the user itself. bleenc can be used also for search and find by light application. So using the snapshot location, it is possible to have a room accuracy in finding where a certain asset is parked, for example, in which room you can find an asset. And in case you may have many assets to find, the find by light function is useful to identify the right asset that you are looking for by simply sending a command to the tag that allows to activate a signal that can be also in this case a LED flashing on the tag, so that uniquely identify the tag that you are going to pick up. bleenc also has a native support for a solution that is used for gate detection. So gate detection is essentially a solution that allows to monitor portals in order to identify entry or exit of people or assets that were bleenc tags. And the portals are realized by pairs of gateways that are installed at all the entrances that to be monitored. And this function provides a real-time identification of each transit with the indication of the direction. So if it is an entry or an exit. So this allows also to have a sort of fence detection by providing real-time monitoring of all the gates within an office or a building. This function can be used either for pedestrian access control, so for staff or guests, but also for vehicle access control. Other interesting application of bleenc are related to safety for man down or a lone worker application. For instance, bleenc tags include a man down detection algorithm. And when man down event is detected, a local alert is generated in the device. The alert is a sort of vibration on the wearable tag. If the worker press the button, it can cancel the alert. But in case there is no pressure of the button, the device sends a high priority notification. So this means that the alarm is again transmitted with HAC request. So this provides 100% safety that packet is delivered. And also in this case, the tag, the alarm is provided with the location information. So you know where the man down event is being realized. Another different implementation of safety solution is, for instance, for lone workers. In this case, it can be implemented by using bidirectional communication. So in this case, instead of detecting the alarm inside the tag, we can monitor the tag from the software, and we can periodically, or in case of anomalies, for instance, in case of lack of movement, send a trigger command to the bleenc tag. This trigger can enable, for instance, a vibration on the tag itself. And in this case, when the wearable vibrates, the operator can press the button to notify he or she is okay. If there is no feedback from the operator, in this case, the alarm is generated. So this is a different type of safety application which relies on the bidirectional communication that is supported by bleenc. And finally, another interesting use case that can be implemented with bleenc, it's based on the use of e-paper displays, in this case referring to managing production within, for example, a manufacturing plant, where semi-finished products are moved in containers. These containers can be equipped with a paper tag that contains order data, for instance, the order number or the quantity. And using the button, the user can notify the completion of a specific process, for instance, and it can be augmented with a snapshot location. But also the label content can be updated during the operation based on the button press and on the location. All these use cases are just listed in order to highlight the features of bleenc, but clearly the range of use cases of application of bleenc is theoretically limitless, and it really depends on the requirements of the market. So with this last slide, this part of the webinar is complete, and so there is time for questions and answers from the audience. Thank you very much.